So this week we started talking about how we could approximate the area between a curve and the x-axis, and we also got into the derivative, in particular the definition of the derivative. Before we start the worksheet, does anyone have any questions on anything other than the worksheet? Okay, so let's start the worksheet. Number one talks about the approximation and the exact area between a function and the x-axis. We have this function. Part A says find two approximations for the area between this function and the x-axis interval 0 to 2 using 4 rectangles. And to do this, you don't necessarily have to draw the function. I will draw the function in a moment. But to find an approximation, you don't need to draw a function, but you do need to know what happens in the interval 0 to 2 when you divide it, in this case, into 4 pieces. So I'm going to mark off 0 and 2 on an interval, and we'll use this to find our two approximations. So in this case, we're dividing it into 4 pieces. So we divide it into 4. The point immediately between 0 and 2 is 1. The point immediately between 0 and 1 is a half, and between 1 and 2 is 1 1/2, which is 3/2. So right here, we've broken our interval 0 to 2 into 4 pieces. If you wanted to find these points algebraically rather than geometrically, we'll observe we're taking the interval 0 to 2, which has length 2, 2 minus 0, dividing that into 4 pieces. So each sub-interval is going to be a half. And to find this first x value, you go from 0 over 1/2. So 0 plus 1/2 is 1/2, and then 1/2 plus another 1/2 gives you 2 halves, which is 1. 1 plus another 1/2, 3 halves. 3 halves plus another 1/2 leaves you at the end of the interval at 2. But either way, we have these x-axis values that we're going to use to find our approximation. Well, to find our approximations. So first, we'll do the left-hand approximation. The left-hand approximation says each of these subintervals we're going to use to define a rectangle. The base of the rectangle will be given by this distance on the x-axis, which in each case is 1/2. And it's the same for all of them, so we can factor that out. But the heights of these rectangles are going to be given by the function evaluated at the left endpoint on each interval. So for 0 to 1/2, we choose the function evaluated at 0. For the next interval, the left endpoint is 1/2. The height of the rectangle will be given by the function evaluated there. And similarly, for the next interval, the left endpoint is 1. The height of the rectangle is determined by the function evaluated there. And on the fourth one, the left endpoint is 3 halves. And the height of the rectangle is given by the function evaluated at 3 halves. Any questions about setting this up so far for the one approximation? So we divide the interval into 4 pieces, and we use the left endpoints here to figure out the heights of the rectangles. Well, now we need f of 0, f of a half, f of 1, f of 3 halves. I'm going to do those as side work over here. F at 0, so 0 minus 0 plus 4. F at a half is 9/4. Why is f of a half 9/4? Well, 1/2 squared is a quarter, minus 4 times a half, so minus a half, plus 4, or minus 4 times a half, what am I doing? Minus 4 times a half, half of 4 is 2, plus 4. So here you get a quarter plus 2. So a quarter plus 8 quarters gives us 9 quarters. f of 1, 1 minus 4 plus 4 is 1, and f of 3/2, f of 3/2, 3/2 squared is 9/4, minus 4 times 3/2, 1.5 of 4 is 6. So negative 4 times 3/2, negative 6 plus 4. And then what is this? It's 9/4 minus 2, which is 1/4. So we have all these x values, or all these y values, and we're just going to substitute them here. F of 0 was 4, f of 1/2 was 9/4, f of 1 is 1, and f of 3/2 is 1/4. Now we just have to add these together, multiply. So what do we get? We get 1/2. 4 and 1 make 5. 9/4 and 1/4 make 10/4, which reduces to 5/2. 5 plus 5.5, 7.5, 15/2. And 15/2 times another half puts another 2 in the denominator. So 15/4. Any questions about the first approximation? Okay, so this one says find both approximations. You may notice on your homework it just says find an approximation. So doing only one on the homework would suffice. But the worksheet says do both, so we have to do both. The right-hand approximation, instead of using the left endpoints on each of these intervals, we're going to use the right endpoints. So on 0 to 1/2, we'll use 1/2. On 1/2 to 1, we'll use 1. On 1 to 3/2, we'll use 3/2. On 3/2 to 2, we'll use 2, the right endpoint. And we're going to use them to define the height of the rectangle. But as before, the base of the rectangle in each case is going to be 1/2, which we can factor out. And then we just need f of 1/2 plus f of 1 plus f of 3/2 plus f of 2. So we use the right endpoints instead, and we have most of those values up here. We don't have f of 2. F of 2 is 0 here because you get what, 4 minus 8 plus 4, so 0. So what do we get? We get 1/2 times f of 1/2 is 9/4. F of 1 is 1. F of the next number is 1/4, and f of 2 is 0, so I'm not even going to write that. That equals 7/4, is that right? So 9/4 plus 1/4, 10/4 reduces to 5/2. 5/2 plus 1, 7/2, and 7/2 times that other half is 7/4. So any questions about 1A? Before doing 1B, I have a question. In 1A, L4 gives an blank approximation, and R4 gives an blank approximation. So the question would be, does L4 give an over approximation or an under approximation of the exact area? And does R4 give an over approximation or an under approximation of the exact area? Well, one way to do this would be to draw our function and draw the rectangles. So maybe I shouldn't have erased the function. I should have erased, I guess, this. May, for non-negative functions, be able to make an observation with that. I'll do it this way. In general, this would be the way to do it. So our function was x squared minus 4x plus 4. Let's graph that function. Conveniently, it's already a perfect square. If it weren't, we'd have to complete the square to figure out how to shift this x squared function. So if we know the graph looks like this, well, this function is just x squared shifted over to the right 2 units, where this is the point 2, 0, and it's just x squared like that. So does L4 give an over and under approximation? Well, here's the interval 0 to 2. We're dividing it into 4 pieces. The left-hand approximation rectangles would look like that. So the left-hand approximation would give us, well, maybe I should show the entire thing. The left-hand approximation would give the area of those 4 rectangles, which notice is more than the exact area. So L4, the left-hand approximation, gives an over approximation. And similarly, R4 would give an under approximation. The rectangles would look, that's the last draw. The rectangles for R4. That's also, well, the rectangles for R4 would look like that. That looks like 3 rectangles, but the height of the last one is 0. So that's, and a rectangle with height 0 is just a line, so it has no area. But R4 would give an under approximation, L4 would give an over approximation. And that was not asked on the worksheet, but it is worth observing. So any questions about that? Okay, 1B. Set up 2 formulas which approximate the area between f of x and the x-axis interval. Which interval? 2 to 5, using 7 rectangles. So right here, again, I'm not going to draw the function. We don't need to know what the function looks like, but we do need to know what happens on the interval 2 to 5. So here's 2, here's 5. We're dividing into 7 pieces. So that's 1, 2, 3, 4, 5, 6. That's 7 pieces. Now we need to find these x values. Well, how are we going to find these x values? Well, we have an interval with length 3. The interval from 2 to 5 has length 5 minus 2, length 3. And we're dividing that into 7 pieces. So that tells us the base of each rectangle is 3/7. Well, we can use that to figure out each of these x values. So if this length is 3/7 and we start at 2, well then to get from here to here we need 2 and another 3/7. 2 is 14/7. So for now, I'm just going to write that as 14/7. 2 is 14/7. 14/7 and another 3/7 give us 17/7. 5 is 35/7. That'll become relevant in a moment. But to find the first one, we take this 3/7 and we add that to, in this case, 2. Any questions about finding 17/7? The next one, start here, go over another 3/7. Here we're at 17/7, go over another 3/7. 17/7 plus 3/7 is 20/7. And then we keep doing that. From here to the next one, we add another 3/7. 20 plus 3, 23. From here to the next one, another 3/7. From here to the next one, another 3/7. From here to there, another 3/7. And from here to the last one, we could check that we do, in fact, get 35/7, which reduces to 5. Any questions about finding these values? Because from here, well, before from here, notice when you're doing this, you could kind of check yourself, because these are going to follow a sequence, well, a pattern, I should say. Because each piece has length 3/7. If you write all of these fractions in their unreduced form, meaning make sure the denominator in each case is 7, then you'll notice the numerators just keep increasing by 3. 14 to 17 to 20, 23, 26, 29, 32, 35. I always find it nice in math when you can check your work somewhere in the middle. And right here, you are able to check your work if you write everything with the same denominator. But for our approximations, we're not going to want unreduced fractions, so I'll change them back to 2 and 5. For our approximations, we need 2. Well, we're going to do a left and a right hand. The left hand approximation looks at each subinterval and picks out the left endpoints and uses them to define our rectangles. So here, L7, the one side of the rectangle in each case is 3/7, and then the heights are determined by the function at 2, 17/7, and so on. So we have f of 2 plus f 17/7 plus f at 20/7 plus f at 23/7 plus f at 26/7 plus f at 29/7 plus f at 32/7. And notice, since we're using the left endpoints, we are not going to include our last endpoint because the last subinterval, the left endpoint is over here at 32/7. And when it says set up an equation, that just means get to here. I wouldn't have you substitute 7 numbers into a function unless it was a really easy function to do the substitution. So any questions about setting up the left-hand approximation here? Okay, this one also wants the right-hand approximation. So for that, same thing, except we use the right endpoints. Notice there we are including the function at 5. We're not including the function at 2 for the right-hand approximation. The one side is again 3/7 in each case, and the heights are determined by the right endpoints. So f at 17/7 plus f at 20/7 plus f at 23/7 plus f at 26/7 plus f at 29/7 plus f at 32/7 plus f at the last one, 35/7, which is 5. So this one, and I think that's a lot of writing. So you will notice on the homework, the corresponding question has 5 subintervals. But you can do it for more subintervals. It follows the same general pattern. So any questions about number, what is this, 1B? To set up the formulas just means set them up like this. 1C, find the exact area between the function and the x-axis on the interval 0 to 3. So here we have f of x is x squared. I'm not going to write that. That might be in the way. X squared minus 4x plus 4. So we want the exact area. And here in this interval, we divide the interval into 7 pieces. Well, if we divide the interval into a certain number of pieces, there's gonna, when you make the rectangles, there's gonna be some quantity which is preventing our approximation from being exact. But if we use more and more rectangles, then you'll see that this quantity that's preventing it from being exact will keep getting smaller. And if you let that number of rectangles keep getting larger, then this area approximation is going to keep getting closer to being exact. Meaning, if we let the number of rectangles go to infinity, this approximation will become exact. And that's the calculus in here. Letting the number of rectangles go to infinity will cause these wedges of error to eventually go to 0. Now, what does that look like in an equation? Well, there are several things to keep in mind for one of these. I always like to start by always keeping in mind that we're going to let n be the number of rectangles, and the area is given by the limit as n goes to infinity. Well, n is the number of rectangles. We next need to add up the area of n rectangles, and that's what we're taking the limit of, because we're approximating using n rectangles, and we're letting that number go to infinity. So we let it go to infinity, and next we need to find the combined area of n rectangles. And that's going to be given by a sum. We're letting the sum go from 1 to n, so there are n pieces in the sum. We just have to figure out now the areas of the rectangles. So inside this sum, we are going to have two pieces. One of them is going to be the one side of the rectangle. The other is going to be the other side of the rectangle. So with these, the first things I like to keep in mind, n is the number of rectangles, and inside here, we have two things, and they correspond to the two sides of the rectangles. Any questions about that so far? Okay, so next we have to find what those two things are. Well, here we're on the interval 0 to 3. So there's 0 to 3. I'm going to mark off 4 for now. I might do more. I might not do more. I don't know. We'll see. We have the interval 0 to 3. N here is the number of rectangles. In the previous cases, we had an actual number of rectangles. Now we have a variable number of rectangles. But we could still apply the same reasoning to figure out these x values. How? Well, we have an interval 0 to 3. So we have an interval with length 3, 3 minus 0. We're dividing it now into n pieces. So each of these subintervals is going to have length 3 over n. An interval with length 3 divided into n pieces. Any questions about getting this 3 over n? Okay. Before going back up here, I'm going to find these some of these values. Well, how are we going to find these values? This first one's a 0. The first one is a 0. What would the next one be? Well, each of these pieces has to have length 3 over n. So here is 0. From here to there has to be 3 over n. So 0 plus 3 over n gives us 3 over n. Any questions about that one? Okay, what's the next one? Well, 3 over n over another 3 over n. So we start at 3 over n, we add to that another 3 over n. Well, 3 over n and another 3 over n makes 6 over n. But writing it as 6 over n isn't going to be as useful as writing it in terms of 3 over n. What does that mean? Well, notice here, 6 over n can be rewritten as 3 over n times 2. You can, split 6 as 3 and 2. And because of that, we can think of this next one as not just 6 over n. We can think of it as 3 over n times 2, 3 over n plus itself, because we got there from going from here to here, 3 over n, and then a second 3 over n. So I'm not going to write it as 3 over n plus 3 over n. This 2 is going to become relevant in a moment. But I am going to write it as 3 over n a second time. So right here, we have 6 over n, which is also 2 copies of 3 over n. Any questions about that one? We will see why it's useful to count out our 3 over n's in a moment. But any questions about the next one? This one? Okay, what's the next one? Well, we start here and we go over another 3 over n. We start here and go over another 3 over n. Well, here we have a 6 over n. You go over another 3 over n, that's what, 9 over n? But what if we ignored the 6 over n part? What if we pretended that didn't even exist right there? Well, we have a 3 over n. We have 2 copies of 3 over n here, and we go over another. What does that give us? Well, that gives us a third 3 over n. So we went from here to here, 3 over n, a second 3 over n, a third 3 over n. The next one would be a fourth 3 over n. And you keep going until you reach the end. We're forming n rectangles. So the last one would be n copies of 3 over n, which of course reduces to 3 because n over n cancels. Any question about finding those x values? Okay, I think finding those x values is the hardest part of these and keeping them organized. Now, the formulas that I gave you in 1C and the notation we're using is going to naturally set up a right-hand approximation. You could do it using a left-hand approximation, but you'd have to play a little more with the notation because, well, in the definition, there's an n-1 instead of an n. You don't have to make note in here that you're doing a right-hand approximation, but I mention that because we're eventually going to use the right endpoints. But before that, there's one other number I'd like to see. Right here. This first x value doesn't look like the rest of the x values. It might be useful to make it look like the rest of the x values. Well, we have 2 copies of 3 over n, 3 and 4. Well, right here, there's 1 3 over n. Well, why does that help us? Well, this notation here, letting the sum go from 1 to n, is telling us that we can count through n rectangles. And the way we've arranged our x values here shows how we can count through these rectangles. Because right here, we have a 1, we have a 2, we have a 3, we have a 4, all the way up to n. That corresponds exactly to these I values going from 1 to n. So a general endpoint here would be given by 3 over n times I. And we're letting I go from 1 up to n. Now, how can we use that to help find areas of rectangles? We still need areas of rectangles up there. Well, area of a rectangle is the one side times the other side. What's the one side? Well, what's this side, I guess I should say. The bottom of each rectangle is 3 over n. What's the height of the rectangle? Well, we're going to use these endpoints. We're going to evaluate the function at those ends. You can put like a dot, dot, dot in there if you want. But we're using these values. How can we use those values? Well, the height of the rectangle is given by the function evaluated at each of those points. So we need to evaluate the function at these points. How are we going to do that? Well, we're going to use I to count through these. The 3 over n, notice, exists in all of those x values. The only thing that's changing is the count. So the 3 over n stays the same, and I gets multiplied by each one, and we're letting I go from 1 to n. So instead of writing 3 over n times I, I'm just going to write that as one fraction, 3i over n. So here we have one side times the other, and in the other side, we are counting through these endpoints. Any questions about that setup? Okay, I'm going to erase this number line now because the simplification will take a few lines. So how do we evaluate this? Well, it's a limit. We need to take the limit at some point. Not yet, we have some simplification to do. We also have to get rid of the sum at some point. Again, not yet, we have simplification to do. 3 over n, I'll leave that there for now. And let's first deal with f of 3i over n. Well, f of x is what? X squared minus 4x plus 4. So that's f of x. What's f of 3i over n? Well, it's 3i over n squared minus 4 times 3 over n plus 4. So what does that equal? Well, it will be convenient to simplify this. 3i over n all squared is what? 9i squared over n squared. Negative 4, 3i over n makes negative 12i over n. And 4 is 4. So f of 3i over n equals that quantity. Any questions about that part? So all we did from one equal sign to the next was find f of 3i over n. Now, for the next part, you could jump straight to using those formulas. I tend to prefer to distribute this first. I'm not really sure why, but I always do. So that's what I'm going to do. So you could jump straight to the formulas. I'm going to distribute. We still haven't taken the limit. We still haven't taken the sum. But let's distribute this. Well, 3 over n times that, so 3 and 9 make a 27. I squared is still I squared. N and n squared makes an n cubed. Then we do the same with the rest. 3 and negative 12 makes a negative 36. I is I. N and n make an n squared. 3 over n and 4 make a 12 over n. Any questions about that distribution? So all we did from here to here was distribute that 3 over n through. Now, the way it's written, well, right now or in the previous step, you could get rid of the sum of I squared. You can get rid of the sum of I. You can get rid of the sum of, in that last case, 1. Now, these sums are all in terms of I, meaning for this first piece, we can split that fraction apart as 27 over n cubed and the sum of I squared. So what I like to do with this is pretty much take out everything but the I squared, write that down first so that I have it, and then deal with the sum. Sum of I squared is given by n plus 1, 2n plus 1 over 6. So this first piece, pull out the 27 over n squared, and the sum of I squared is that piece. Any questions about that first part? Okay, so now we have to do that with the other two parts. This part is just the sum of I, but before that we have this negative 36, and we have an n squared in the bottom. The sum of I is given on that page, n times n plus 1 over 2. And then this last piece, and we usually don't write the 1, but it is the sum of 12 over n from 1 to n. So you could think of that as 12 over n times 1. But either way, we would have a 12 over n, and then the sum of 1 is given on that page. The sum of 1 is n. So in that step, we were able to get rid of the sums and the i's by using those three formulas. Any questions about that step? Okay. Now, how can we evaluate this limit? Well, we have our observation from last week's workshop. And to illustrate that, I'm going to look at this term first. What would happen if we, well, first, we have a limit as n goes to infinity, and we have some polynomials. Let's write this as one fraction, this one piece. What would that look like? Well, on the bottom, you have 2n squared. On the top, you have n squared, or n squared plus n, with a negative 36 on it. So that makes negative 36n squared minus 36n. Well, we're taking the limit as n goes to infinity, but we have here a degree 2 over a degree 2. So how would we do that? Well, we would divide everything by n squared and then take the limit. And then these numbers here would be left. We could do that, or we can make the coefficient argument, which just says that that limit would be that number over that number, which in this case reduces to what? Negative 18. So that middle piece right here, as n goes to infinity, that equals negative 18. Negative 36 over 2. Any questions about that middle piece? Okay, the last piece, well, this fraction 12n over n, and the n's cancel, that fraction, or that multiplies just to 12. As n goes to infinity, 12 doesn't change. So we have just a 12 there. And what about this first piece? Well, what do we have in the denominator? In the denominator, we have 6n cubed. What do we have in the numerator? Well, we have a lot of things we could multiply together. But notice we have an n times something else with an n times something else with an n. And that's going to turn into something in terms of n cubed. So over here we have an n cubed over another n cubed. So we can apply the same type of coefficient argument over here. What's the coefficient on n cubed in the denominator? Well, in the denominator we have a 6. What's the coefficient on n cubed in the numerator? Well, without distributing everything, we can do that just by looking at the coefficients on each n. The way we would get n cubed here is n times 2n. That would give us 2n cubed. But there's also a 27. So the coefficient on n cubed in the numerator, 27 times 1 times 1 times 2. So the coefficients on n cubed in the top, 27 times 2 in the bottom are 6. So that fraction reduces to what? 27 over 3, which is 9. And you add these numbers, and you get the exact area as 3. So any questions on this one? 1C. this computation, I mean, I do think it is the hardest computation we will see. So it will not be on exam 1, but we are going to see this again when we get into chapter 5. And we are going to talk about it again when we get into chapter 5. So if there are things which are unclear now, then maybe in the next discussion in a few weeks, it'll become more clear. But for now, I think the most important things to keep in mind in setting it up are that n is always the number of rectangles. And in this large sum, we have areas of rectangles. One side times the other. So this will not be on exam 1, may show up on the final computation like this. So any questions about problem 1? Okay, before going on to problem 2, I have another question on number 1. And I'd like you to work on it for about a minute to see what you get. Another question about this one, actually. So, what if this question asked, what if 1C asked the same exact question, except it used the interval 1 to 4? And well, I don't mean actually simplify this and solve it, but if the question asked 1 to 4 instead of 0 to 3, what would change in that formula up there? So try that for about a minute and see what you get. So if 1C asks 1 to 4, what up there is different? There is something that's different. There is at least one thing that is different. So see what you can do with that. It may be useful to draw out the interval 1 to 4 and see what happens when you divide that up. So if this question asks 1 to 4, we'll notice the base of each rectangle is still going to be 3 over n. It's still an interval of length 3. We're dividing into n pieces, but this first x-axis point that we mark off, instead of going from 0 to 3 over n, we're starting at 1 and then going over 3 over n. So we have 1 plus 3 over n. What about the next one? Well, the next one would be 1 plus 3 over n plus another 3 over n plus another 3 over n, also known as 1 plus 3 over n times 2. And you can do another argument for the next few endpoints. But the only difference is that inside the function, we're moving over and starting at 1 instead of 0. And this, of course, would lead to a different area. But Well, I was actually incorrect in saying this, of course, will lead to a different area. This one actually leads to the exact same area, which is interesting. But the only difference in the formula is that we move over 1. Any questions about that? I should put the Zoom page back on my screen so I can see. Okay. Any questions about that? So in general, if you did that, the area would be different. So I'll just explain right now. The area between 0 and 3 and 1 and 4 for this one happens to be the same exact area, which is interesting. Why is it the same? Well, parabolas are very symmetric. The area between 1 and 3 is given by that plus the other thing, which in this case equals 3. The area, maybe I should move 3 over. So it looks a little smaller. The area from 0 to 3 would look like that. The area from 1 to 4 would look like this. And by the symmetry of the parabola, in terms of area, this wedge has the same area as that, and this has the same area as that. That's I did not set it up so that they would be the same. More on that in chapter 5. But let's next go to number 2 on this question, or on this worksheet, which says approximate the area between sine x and the x-axis interval 0 to pi over 2 using 3 rectangles. So, well, we have sine x. We're looking at the interval 0 to pi over 2. And we want to use 3 rectangles. So we're again going to divide this up. This time we're dividing it into 3 pieces. How are we going to find these endpoints? Well, the length of this interval, pi over 2 minus 0 is pi over 2. We're dividing that into 3 pieces. Pi over 2 minus 0 is pi over 2. Divide that into 3. And you get pi over 6. Wow. If each of these lengths is pi over 6, then this one is 0 plus pi over 6, which is pi over 6. The next one is pi over 6 plus pi over 6, which is pi over 3, 2 pi over 6, pi over 3. And the last one, pi over 6, or 2 pi over 6 plus another pi over 6, 3 pi over 6, which is pi over 2. Any questions about getting those x values? So now we need to set up our approximations and simplify them. So here L3 would equal what? The one side times the other. The one side is always pi over 6. The heights here are given by the left endpoints. So f of 0 plus f of pi over 6 plus f of pi over 3. And we need to find what those are. I'm going to do the side work over here. F of 0 is sine of 0. Sine of 0 is 0. Why is it 0? Because that point over there is 1, 0, so sine of 0 is the y value. Next, we need sine of pi over 6. Sine of pi over 6. Well, we have this triangle quadrant 1 angle. Pi over 6, 1 to root 3 to 2, pi over 3. So sine of pi over 6 is what? Opposite over hypotenuse for that angle. Opposite is 1, hypotenuse is 2. Next, we need sine of pi over 3. We have this triangle, which is convenient. Sine of pi over 3. Opposite over hypotenuse for that angle. Opposite is root 3, hypotenuse is 2. we're eventually going to need sine of pi over 2, so I'm just going to do that now. Sine of pi over 2 is given by the y value for that point up there, which is 1. So sine of pi over 2 is 1. Well, what do we get for this approximation now? Pi over 6 times f of 0, which is 0, f of pi over 6, which is a half, plus f of 3, f of pi over 3, root 3 over 2. And the inside of this quantity does simplify a little. Maybe I should use a non-square parentheses. So it's what? It's root 3 plus 1 over 2. They have the same denominator. So just root 3 plus 1 over 2. And you can leave your answer like that. You could distribute it through if you want as pi root 3 plus pi over 12. Or you could do pi times root 3 plus 1 over 12. I mean, whichever way you want. But the decimal is incorrect. Any questions about the left-hand approximation here? An answer like this is perfectly fine. That's a number, just like that's a number. But now we need the other approximation. The one side is again given by pi over 6, but instead of starting at 0, we're going to start here and end over at pi over 2. So we need f of pi over 6 plus f of pi over 3 plus f of pi over 2. So what do we have here? F of pi over 6 is a half. F of pi over 3 is root 3 over 2. F of pi over 2 is 1. And now adding these together, 1 and 1/2 makes 3 halves. 3 halves plus root 3 is 3 plus root 3. Half is still a half, and pi over 6 we can just leave out there. Any questions about this one? So on the first exam does cover the first 5 weeks. And the first week of homework had questions like evaluate sine of whatever and cosine and so on. On the test, there won't be any questions which say evaluate sine of this, but you could still need to know how to do them in a problem like this. The first test will be largely the calculus we've done. And in doing the calculus we've done, limits and approximations and derivatives, which we'll do in a moment. In doing that calculus, you may have to evaluate some trig functions at points. Any questions about this one? Okay, next, what do we have next? 5x squared 2x minus 3. So these last two questions get into the derivative. And the derivative we will be seeing for the next 6, 7, 8 weeks of this course. And we start by defining the derivative. We define the derivative, well, first, the derivative is a new function. So given a function, we can use this definition to create an entirely different function, which has a nice interpretation, has many nice interpretations. The way we set it up was so that the derivative, so here's a function, the derivative of that function will give us the slopes of tangent lines, the slope of that line. At any x value, it'll give us the slope of a tangent line. And we defined it so that it would do that. And here, we're going to use that definition to find this new function. And then we're going to use it a couple times in parts B and C. So what is the definition? Well, the definition says f prime of x, a new function, equals the limit as h approaches 0 of f of x plus h minus f of x all over h. And to set this up, we found slopes of secant lines, and then in the limit, we saw that they approached slopes of tangent lines, which we wanted. So here we need to find this quantity for this function. And part A tells us that should simplify to 10 plus 2x. So let's do that. Limit h approaches 0. We need f of x plus h. So there's f of x. F of x plus h replaces all x's with x plus h. So right here, our function was 5x squared, 2x minus 3. Replace all x's with x plus h. You get 5 times x plus h all squared, plus 2, x plus h, and then minus 3 stays minus 3. So any questions about getting f of x plus h? So here, we're using this function to help find another function. Okay. Now we need to subtract f of x. So minus f of x. So just subtract all of f of x. And we do want to subtract all of f of x so that the algebra works out. If you don't subtract all of f of x, the algebra won't work out. And this is all divided by h. So any questions about setting this one up? Okay, now we need to take the limit. But notice if you let h equal 0, you get a 0 over 0. And when that happens, we need to do some algebra. What algebra can we do? Well, there's a good amount of algebra we can do. We can deal with this x plus h squared. X plus h squared, side work. X plus h squared is that, x squared plus 2xh plus h squared. But we want 5 of them. So we want 5 times all of that. So 5 of those gives us 5x squared, 10xh, and 5h squared. Well, okay, that's some algebra we can do. What else do we do? Well, we can distribute that too. So we have 2x and 2h. There's nothing we can do with that negative 3, except be sure that we write it. What else do we have? Negative 5x squared. Let's distribute this negative. Negative 5x squared, negative 2x, and negative of negative 3, which is positive 3. That's a bad h. So we simplify the numerator and we have all of that. Does that help us? Well, it does. How does it help us? Well, let's look at what we have. We have here a 5x squared and a negative 5x squared. Well, that adds to 0. We have a 2x and a negative 2x. That also adds to 0. We have a negative 3 and a positive 3. Those also add to 0. So everything in that numerator that's currently shaped adds to 0. And what are we left with? Notice we still haven't taken the limit. What are we left with? Well, on the top, we're left with 10xh. We're left with 5h squared. We're left with 2h. And in the denominator, we still have that h there. Any questions about that step in simplification? So everything up there, well, all these 6 terms added to 0 left with this. Again, you let h equals 0 down here, you get a 0 over 0. But notice all of these terms have an h on them. So we can cancel an h from each term. What happens if we cancel an h from that? Well, we have 10x. What happens if we cancel an h from that? We have a 5 and an h. What happens if we cancel an h from that? All we have left is that 2. In the denominator, if you cancel an h, you have a 1. So I'm not even going to write that. But now, we still have the limit as h approaches 0. And now we can let h equal 0. We get 10x plus 0 plus 2. The definition of the derivative is very important. So we'll be next week, we will learn a way that we can go from here down to here in essentially one step. But the definition of this derivative is very important because for most of the next 7-8 weeks, we won't really be talking much about limits. But behind everything we do for the next, well, really for the rest of the semester, behind everything we do is this limit. And the derivative very nicely ties in the last 2.5 months of the course to the first month of the course when we talked about limits. So there will be a question on exam 1 that says use the definition of the derivative. And when it says use the definition of the derivative, you have to use the definition of the derivative, unless you don't want credit. And there will be a question like that on the first exam, 100%. There will 100% be a question like that on the final exam. The definition is very important. Any questions about that? Well, any questions about part A? If it doesn't say use the definition, you don't have to use the definition. But to this point, all we have is the definition. Okay, part B. Find equation for the line tangent to f of x when x equals -1. Well, we need a tangent line. Well, we need a line. So we need a point and a slope. We need a point and a slope. What is it? B. Point. Slope. What's the point? Well, x equals -1. What's y when x equals -1? Well, let x equal -1 up there. Let x equal -1 up there. You get 5 times 1, which is 5, minus 2, minus 3. 5 minus 2 is 3. 3 minus 3 is 0. So the point here is -1, 0. Any questions about finding the point? What about the slope? Well, the derivative is set up to give us the slope of tangent lines. Well, the slope of, tangent lines, any tangent line. I don't know where this function is. It's a parabola. Let's just say it looks something like this. That's very inaccurate. Maybe it's not. It's only slightly inaccurate. But I should draw it so that -1 is more magnified than the first quadrant. This function, it's some sort of parabola. It goes somewhere. What we're looking for, here's -1. What we're looking for is the equation for that tangent line. Well, the point, notice, is on the intersection of the line and the function. So we can use the function to find the point. But what's the slope? Well, remember, the derivative is set up to give us the slope of that tangent line. So if we want the slope of the tangent line at -1, all we need is to evaluate the derivative at x equals -1. And what do we get? -10 plus 2, which is -8. And from here, we get our equation for the line. Y minus the y value was negative 8x minus negative 1, x plus 1. And then I don't like writing zeros like that, so I'll write it like that. You could leave it in the first way if you want. I don't like writing zeros. So the function gives us the point we need, and the derivative gives us the slope we need. Any questions about 1b, not 1b, 3b? Okay, 3c says what? Find all x values at which f of x has a horizontal tangent. Well, what does a horizontal tangent look like? It looks like, if here's a function, a horizontal tangent is a tangent line that's horizontal. And the slope of a horizontal line is 0. So we need the x values at which the function has a tangent line with slope 0. So for part C, all we need to do is set the derivative equal to 0 and find the x value. So here the derivative, 10x plus 2. Set that equal to 0, solve for x. What do we get? X equals, subtract 2, divide by 10. Negative 2/10 reduces to negative 1/5. Any questions about 1c? So next week we will, well, not I guess after the first test, we will learn another way to interpret the derivative. But for now, we're going to keep in mind the derivative gives us slopes of tangent lines. So any questions about number 3? Okay, number 4 says use the definition of the derivative to find the derivative of what, x to the 5th plus 2? Or was it minus 2? Plus 2. So use the definition of the derivative to find f prime x here. The answer will turn out to be 5x to the 4th, which is noted. Now, for these questions where I say use the definition, I usually do, at least for now, say what the answer should eventually be. And that's usually because I followed up with a tangent line question. And if you don't get the derivative portion right, I still want you to be able to get the tangent line portion correct. So here, we know that this limit should simplify to x to the, or 5x to the 4th. Well, does it? Well, yes. Why does it? Well, let's see. F of x plus h, x plus h to the 5th plus 2 minus f of x. Well, let's subtract f of x. So we have that. No, I'm not going to do that to you now. I was going to see what goes wrong there, but I don't want to do that. There's not too much time left. Make sure you subtract all of f of x. If I didn't subtract all of it, we'd have 2 plus 2, which is 4, which won't eventually cancel out with an h. Make sure you subtract all of f of x. Now, how do we simplify this? Well, we need to expand this quantity to the 5th. How do we do that? Well, you could multiply out x plus h times x plus h times x plus h and so on. I would prefer to use Pascal's triangle because it takes less time. So here we start with 1s in that arrangement, and then we form the next row by adding the 2 numbers above it. It starts and ends with a 1 in between on this 3rd row. 1 plus 1 is 2. For the next row, start with a 1. 1 plus 2 is 3. 2 plus 1 is another 3. And 1 is 1. We need to do this until the second number is 5, because we have something raised to the 5th. So what do we get? 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And with a 1, that's not a 5. We need another row. Start with a 1. 1 plus 4 is 5. Well, that means this row is going to give us what we want. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And it ends with a 1. So we have this row, which gives us our coefficients. I'm going to do the side work for this down here and then just write the answer up here. So we have our coefficients: 1, positive 5, positive 10, positive 10, positive 5, positive 1. And now we look at our two terms here. We have an x and an h. The first one, we put 5 of on the first thing and then keep going down by 1. Meaning, first one, we put x to the 5th, and then the next one, x to the 4th, x to the 3rd, x to the 2, x to the 1, x to the 0. Then we do the same thing with this other piece, except in the opposite order. So the other thing is h. We put 0 of them here, 1 of them here, 2, 3, 4, and 5. That's an h. And now we just write that up here without all the ones all over the place. So 1 times x to the 5th times 1, x to the 5th, plus 5, x to the 4, h, plus 10, x cubed, h squared, plus 10, x squared, h cubed, plus 5, x, h to the 4, plus h to the 5th. Well, that's what this first thing equals. The rest of it just stays there, so I'm just going to write positive 2, negative x to the 5th, and a negative 2. And then the h in the bottom is still there. Any questions about getting to that line? I guess I'm going to go about 1 minute over. But we are almost done with this. We can't substitute h equals 0 yet, but we can notice some of the things cancel. X to the 5th, negative x to the 5th, cancel. Also 2 and negative 2, cancel. They add to 0. And what are we left with? Well, we're left with everything in the middle here divided by h. Notice all of these terms have an h. So we can cancel an h from everything. And what are we left with if we do that? 5x to the 4th times h to the 0, which is 1, plus 10x cubed h. Removing h from everything, plus 10x squared, h squared, plus 5x h cubed, plus h to the 4. Cancel an h, it's all divided by 1. And now we can let h go to 0. If h goes to 0, this piece doesn't change, and all of those other things go to 0. So we do get the answer we were supposed to get. Any questions about this one? On a test, if you have one of these, which you will have one of them, the largest exponent I've ever put on a test is a 3. So you can expect to not have an exponent 4 or an exponent of 5. So any questions about this? Okay, well, yeah, okay, I went over by a minute. So we have a homework assignment due on Monday. So if you have any questions on that, just let me know over the weekend or today or tomorrow. But until then, I hope you enjoy your Thursday and your weekend, and I'll see you next week. Thank you for coming.